Okay, good morning.
Morning, Sensei.
Okay, shall we start? So how are you? It's very hot. And the typhoon is coming. So we cannot go anywhere. Okay, so Zafira-san, you start first.
Today I don't have anything. I see you do my correction, Sensei. So I can pass to next person.
Okay. So who will be the next? Sarah-san, you have something to show me?
Yes, I have.
Okay.
Okay. I wanna show you the displacement and basic design method DBDM. I just checked about the steel beam 750 and 750.
Sarah,
And-
sorry. I think you doesn't share the screen. We cannot see the screen.
Why?
Can you try again?
Okay. How about it?
No.
No.
Are you sharing
Yeah.
with computer or iPad?
Computer.
But we cannot see the screen.
Mm,
Maybe Sarah want to start first. Sarah-san?
Okay, so shall we move to next person?
Okay.
Zafira-san, I would like to explain
Hi.
about your paper.
Okay, Sensei.
Is it okay?
Yes, yes.
I will share my screen. Okay. So the main part is yeah. So this is the explanation about displacement-based design method. So this is only text, no
Yes.
figure.
Okay.
So it's not so easy for
People to understand.
people to understand.
Mhm.
So I was thinking, well, it's okay this part, but so how to say? So I want to, my idea is to start from coupled wall with steel beam. Steel beam. So you obtain this figure
Yes.
based on, by displacement-based design. So you can explain step by step
Okay.
how to obtain this figure following this procedure.
Okay. Understand.
Is there any limitation of the number of pages?
I think it's 10, Sensei.
10. So
Yes.
right now, how many?
It's already 10 pages, but I will try to simplify if there are some words I can simplify.
Okay. Maybe you can need to explain this one.
Okay.
Yeah, maybe you can start directly from
Still good.
steel beam.
Okay.
And you can say steel beam, you design steel beam, to satisfy 1/250 design criteria.
Okay.
Then this is a result of story drift. Yeah. And okay, there is no time history analysis for steel beam, right?
This one figure 6 is time history analysis. Sensei.
Time history analysis is
Underneath, no, only for damper.
yeah, only for damper. Okay. So 5.2 is a steel beam with metallic damper. And this is okay. Well, both design is a little bit lower than capacity curve.
Mhm.
So what is the conclusion for this?
Conclusion, if compared to the time history analysis,
Mm.
the limit is also less than the limit. If you
Mhm.
scroll down to time history analysis,
Analysis.
this one.
Uh,
Yeah. So for L Central, it's less than limit, but Kobe is only like touch the like
Mhm.
little bit more. So
Here you compare 180, 60, 40, 20.
yeah, same.
And this one is
I only present from 100 to only 120, the biggest and the lowest, because if I put
okay.
everything, cannot fit. Yeah.
Okay.
Mm.
And in case of viscoelastic, 100% somehow
It's not good.
Yeah.
Not good. Yeah.
And time history analysis, this one.
Yes. If we see the blue line, 100 is is over the limit
Okay.
for L Central.
Mm-hmm.
But 500 and 1000 is less than the limit.
Okay. And combination is
This one says it.
this one, hybrid damper, right? And this one, okay. And hybrid damper is time history, this one?
Yes.
Okay, good. So I think, paper is, well, I want to suggest include time history analysis in each section. So section 5.2, steel beam with metallic damper. So first you show the result of displacement design. Then you compare with time history analysis.
Okay. So the time history analysis, I just delete and then just combine with the
Yeah.
Okay.
I think it makes the story more simple.
Okay, sensei.
Easy to understand. Yeah.
Right.
Okay. Yeah. So after you made a correction, please send me again.
Hi. Okay. Thank you,
Okay.
sensei.
So let's see. Ataya-san, do you have anything you can explain?
Since I have nothing, but last time I sent the corrected paper, as you told me to send you back, but I didn't get any feedback.
Oh, really?
Yeah.
I think nothing to correct, maybe. It is a paper of JES, right?
Yes, Sensei.
I think nothing to correct. Yeah. So you can submit, maybe.
The deadline for submission is 22, right, sensei? And I think before I check in the website, before we submit, we have to register first.
Mm-hmm.
Yeah.
Oh, okay.
I will ask Majima how to register and pay for the fee. Thank you, sensei.
let me see. あたやさんね。ちょっと待ってよ。So, Ataya-san, when you start internship?
I already started. Yes.
Okay. So when did you start?
1st August, Sensei.
1st August.
Yes.
And it continues to how long?
2 months. It will end at the end of September, 29-30.
Oh, end of September.
Yes.
So how it's going? It's okay?
Yes, Sensei, it's fine.
What kind of work are you doing?
Up to this moment, they gave me some lecture information about safety,
Mm,
about building modeling information, information modeling, and some drawings. But mostly it was focused about safety.
Safety. So you communicate with by Japanese or English?
Actually, they explain in Japanese, but it's difficult as much as I understand. And sometimes we use Google Translate. Difficult.
Okay. Yeah. So, but you should continue to learn Japanese language.
Yes, Sensei.
Okay. So maybe this is the latest version of your JES paper.
Yes, Sensei. I corrected based on your comments. Maybe this is that file.
Yeah, I think you can submit. I think there is nothing to correct. Okay, so yeah, so it's on 9 pages. It's 9 pages, okay? I mean,
Yes, since it is because the maximum is 10, and they also talked about a cover letter. So I sent them an email about is there any specific template about the cover letter, or when we submit the paper, should the cover letter combined with the main file, or they have to be separated?
And what they said?
They said that there is no any specific template for cover letter, and for submitting you have to combine the cover letter with the main text. So with the cover letter and main text, it would be 10 pages, Sensei.
What information you should write in cover letter?
Because they didn't tell me about any specific template, so I wanted since I send you a cover letter for comment. Maybe because they said there's no any specific template, so maybe we can prepare it based on some other conventional templates that students send to other journal papers, maybe.
Actually, I mean, how to say, Japanese, well, how to say, they accept mainly Japanese paper, but in Japanese, and also they accept paper in English. And there are two templates. One is for templates for Japanese paper, and in Japanese paper, there is no cover letter.
Yes, Sensei, but in the template that they put on the website for English version, they mentioned that there has to be cover letter.
Well, maybe they copy the template from some other journal and they forgot to delete the template.
But again, since I have their email, their reply, they said that for the is there any specific template for a cover sheet? It was my question. Your answer is there is no specific template for a cover sheet. Number two, should the cover sheet and paper be combined in one file or separate? Answer, please, the cover sheet and paper should be combined in one file.
Oh, really?
Yeah,
Okay.
so there have this answer shows that the cover letter is needed. I received a template from Saranya-san. Maybe I can edit something about cover sheet and send you, Sensei.
Okay. This is a sample. There's no cover letter starting from Abun template. How about this one? こっちなのか。Okay, well, anyway. Sorry, maybe I made a mistake. This is very old date. ちょっと待って。Maybe I made a mistake. 音楽チェント10の。Okay, this one. Website. And どっちもどれこう。チェックしてよこう。Okay, so this is a sample typing instruction. Okay, so they have an instruction only for main page. Okay, and how to apply? So August 22nd is the deadline.
Yes.
And, you must say some amount of fee. Okay. Okay, we still have time, so let's discuss later. How to apply. Yeah. ちょっと結構いい値段だな。Very expensive. But not so expensive compared to other conference. Okay. サラさん、could you try again? So Ataya-san, you don't have anything to explain.
No, Sensei, just maybe I send you the cover letter later.
Yeah. Okay.
Okay, thank you.
And please concentrate on, internship.
Yeah, thank you, Sensei.
And I'm happy to see you. And so do you enjoy? You are the only foreigner in the company?
There's two others, Sensei.
Two others. Okay.
Myanmar and Vietnam.
Okay. They can speak Japanese?
Yes, they have, both of them have N1, Sensei.
Better than you.
Yeah, no employee, I'm only the intern.
Okay. So, okay, good. Okay, Sarah-san,
Yes.
could you try again?
Okay. You
are sharing screen. Okay. It's coming. Yeah. Okay, I can see.
Okay.
Yeah.
Okay, now I'm gonna talk about displacement basic design method. I checked the still being 750 and 750. First of all, this is 1 divided by 100. From this, I found the target drift angle at the top. This one is 0.000, and
is it 100 or 250?
This one?
No. Response
Mm.
structure of 1/100.
Yes. This one is 1 divided by 100. And from this, we put in this target drift in this one in the cyclic. 1 divided by 250. And
Okay. So you conduct pushover until 1/100 story drift. Maybe this is the meaning. And this 1 point, 待って、I cannot put right view option. How can I write down comment?
okay, from this we find the a point for 484. From this we I found this this one. This is top story of the and I put in the stereo 3D in of the 1 divided by 250. It is a cyclic, and so it is a cyclic.
Oh, okay. Okay.
Okay. And from this, it is a energy of sloping. This is cyclics. And from this, we find the properties of CDOF. And for about the ductility, it is for about wall of the ductility, it is less than 1. It is 0.05, and for about beam of ductility, it is all of them are less than 1, so it will be 0.05.
Okay. Yeah.
Okay. So use this formula. Is it? And from this, we find on the CD of F. And but result is was reserved. Target line bigger than the capacity curve.
Why blue line is extending to 0.0 more than 0.06? Is it okay?
Yes. Okay, I will show you. This is displacement 0.067.
This is the displacement of equivalent single degree of freedom. Is that correct?
Yes.
It's 1
This
over
is the
250.
target displacement. So actually, Sarah-san, your capacity curve, you should take from 1/100 because this is 1/250 is too short. So if you use 100 over 1/100, the capacity curve will be longer. And if you can see here, the target line of the target design is more like over the capacity curve. Mean the design is not how can I say, the design is not good. So next time please use the capacity curve for 1/100.
Okay.
Yeah, this is you put the wrong data here.
Okay.
Sorry, I don't still understand why you, well, it's confusing. 1 over 100 or 1 over 250? Which one?
For actually, since she start from 100, 1 over 100 for the
Mm.
pushover to get the top story drift,
Yeah,
and then after that he used the top story drift to do the cyclic for 1 over 250.
Okay.
But inside here, the Sarah-san, can you like make it smaller? Okay, so from 1 over 250 from the cyclic, she took the energy from the
Yeah,
each member
yeah.
and then calculate for the damping, equivalent damping,
Mm.
and then to plot this capacity curve and the target design. So basically this structure, because this is 15 story, so 15 story, it doesn't satisfy with the capacity curve. So the target drift actually is over than the capacity curve. In the capacity curve here, she should put the structure response 1 over 100. So the capacity curve will be longer. So this one is capacity curve
Why?
from
Why?
cycle.
This straight line should be, terminated at 1 over 250. I don't know. So you try to design the building to satisfy 1 over 100, 1 over 250 story drift.
The target line is from the calculation on the left side. It's nothing to do from the structure response, only the capacity curve from structure response.
Okay.
I think she has some error in input data. I will check later since.
Okay. Okay, good. So please continue. And
Yeah. This is the result, Sensei. Oh,
there are many screens.
this
Okay.
is Sensei. This is last result.
Yeah.
So yeah, that's
We
it.
discuss later, Sarah. It's okay.
Okay. Okay, Sarah-san, please continue. And please discuss with Zafira-san.
That's it, Sensei.
Okay.
Yeah, from this, I understand target line is bigger than capacity curve. So I thought, and the result was reserved.
Okay. We discuss later, Sarah.
Yeah. Okay, Sarah-san,
Thank
thank you. So you can
Okay.
close your window.
Okay.
Okay. So now, Saraya-san, so shall we have could you make your presentation?
Yes, Sensei, sure. I will share my screen.
Yeah.
I hope my screen is visible, Sensei.
Yeah, I can see.
Okay. So, Sensei, from the last meeting, I actually completed the base isolation design of my hybrid control system. And now I am moving forward to the second part of the optimization, where I will design the tune mass damper.
Okay.
So before doing that, now, as we had discussed earlier, now I will make the structure a single degree of freedom system so that it is optimization is faster. And also because of the base isolation, it can be idealized as a single degree of freedom system. So here I have only considered one mass, and that is isolated with the unbonded isolators. And first, after developing the single degree of freedom system codes, I have validated that with the multi-degree of freedom system using MATLAB. So this is the acceleration response of the, I will just open the pointer. Yeah. So this is the acceleration response of the structure of the 8-story hospital building, where this is the top story acceleration response using the multi-degree of freedom system, as compared to the single degree of freedom system, only mass acceleration response. So it is matching quite nicely. Only the higher frequency terms are not there because of the reduced degrees of freedom. And the base displacement is actually matching completely because it is not affected much from the higher degrees of freedom. So this was for the unbonded isolator case without TMD. Then I have also matched it with 1 TMD at the base. So these are actually all the different codes that I have developed for the optimization problem. So before executing that, I wanted to be sure that the codes are correct. So so this is with the unbonded isolators and one more TMD at the base. So this structure is actually a single mass, which is connected to the ground by the unbonded isolator, and one TMD is added to the single mass. That is, this is a 2-degree of freedom system, where I have plotted the main degree of freedom system acceleration and displacement mass. So again, the matching is quite good with 1 TMD at the base. Similar results I have got with 2 TMD, one at the base, one at the top. So in case of the single degree of freedom system, it is actually one mass and 2 TMDs are connected to that one mass. But in case of the multi-degree of freedom system, 1 TMD is at the top story and 1 TMD is at the base mass. So again, the results are matching quite nicely. There is only slight difference. This is because now the both the TMDs are attached to the same mass, and not in the case of multi-degree of freedom system, there was only 1 TMD at the base mass, but now both the TMDs are attached to the same mass. So I think this is okay. So this slight difference should come in the results. So now again, one more check I wanted to do is that in my codes, if I am using 1 TMD, say of 10% mass ratio, or say at the base floor, 1 TMD at 10% mass ratio, say at the top floor, and 2 TMDs of 5% and 5% mass ratio. So I wanted to check if all those are giving the same results. So yes, they are giving the same results. So my single degree of freedom system models are validated. This was for the earthquakes. Now for the winds also, I am getting good validation. There are slight differences. I think this is because, like, for wind, you require very small time steps. So if I refine it further, this differences will reduce. But I think it is more or less validated for wind. For unbonded isolators, for with TMD at the base, TMD at the 2 TMDs at the base and the top, and also the different TMD designs. So after doing all these validations, I have like accepted the single degree of freedom model code, and now I have tried to do the optimization. So these were the like 20 earthquakes that I had selected. These 20 will be 20 set of maximum considered earthquake, or like strong earthquake, and also 20 moderate earthquakes. But the records are same for the 20. So with this, the first one, the Imperial Valley earthquake, I first wanted to check whether in this earthquake how my optimization works. Then I would do for all the earthquakes. So again, one thing that I found is, like, when I designed the isolation system, considering the nonlinear Stera models, the base displacement was slightly reduced because there was more like a response in the superstructure and lesser response in the base displacement. So now for the single degree of freedom system, the base displacement is slightly increased. So to counter that, I had to like make some small modifications in the design of the isolation system again, where I have slightly reduced the isolation period from 7 seconds to 6.75 seconds. And like more or less the layout of the details are same, but only there is a slight reduction in the isolation time period. And now with this isolation system, I had tried to use the Bayesian optimization method, where I have used 3 different variables. One is the mass ratio of one of the TMDs, the damping ratios of the first TMD, damping ratio of the second TMD, and the total mass ratio. I have used this as a constant, like this is a input that I am giving. So I have considered a total mass ratio of 10%, and I have optimized these 3 variables for only this one earthquake scenario, only this Imperial Valley earthquake scenario. So now I have found the results of the optimization. So this is the results of the optimization. Here, the time period, input time period, I have given this as an input, because this is corresponding to the second time period of the isolation system and the first time period of the isolation system. So basically, in the multi-degree of freedom framework, this second time period will be the TMD at the top, and the first time period will be the TMD at the base. So from our understanding from the last study also, in case of earthquake, it is expected that we should only have one TMD at the base floor and no TMD at the top to reduce the base displacement. So our results are also similar. And here the ranges of the different variables I have selected as, say this is, if this is 0.1, maximum is 0.1. I have not used 0 here, because if I use 0, there are some numerical errors in the code, because sometimes we divide by the mass. So 0 mass will not work. So I have used very small mass, say 0.01 mass ratio to 0.1. Minus 1.1 minus 0.01. So this is the range of mass ratio. For damping ratio, I have used from 0 to 50% damping in both the cases. So the results that I have obtained is like this. For mass ratio, actually we are considering, like, the results are obtained as 98 or 99% of the total mass should be accumulated in the base floor. So this also matches with our understanding that yes, if it is only earthquake scenario, then all the mass should be concentrated at the base floor. So this is coming from the results as well. And the tuning ratio, I have selected 1:1 as we have decided for the tuning criteria. And the damping ratio, we are finding that it's like 1% for the 1% for the TMD at the base and 10% for the TMD at the top. But if the mass ratio is so small, so we can even like neglect the TMD at the top. So only one TMD. So the optimization results show that we should use only one TMD with 1% damping ratio at the base floor. So this is coming from the optimization by minimizing the peak displacement of the peak base displacement. So the maximum was 870 millimeter. Now it has come down to 572 millimeter from the optimization process. But there again, one problem which I noted here is like there is so many significant figures after the so many significant figures in the optimization variables. So what I felt is there could be a scenario when the optimization becomes very local and it will not take a global scenario, because there are so many options available for the number of significant figures. So what I planned is like we can try to reduce the significant figures to 2 if we take the optimization as an integer, and we try to get only integer values from 1 to 99. And inside the code, what I do is I divide that by 1000.
Okay.
So this I have divided by 1000. This I have divided by 1000. And then the damping ratio also 0 to 50% I have divided by 100. So this is actually the percentage damping ratio. So now we will only get values like 1%, 2%, and not 1.5%.
Okay.
So, and I think this is okay, because when we are designing also, we will not design to so much like this significant figures. So I think this will give like a more better solution and maybe faster, because the solutions are lesser now. There is only 99 values here, 50 values there, and 50 values there. So again, I have tried to optimize. Again, I have got similar results as in the case of the earlier case, but now we are getting like whole numbers, 99 by 1000, like 0.099, so almost 10% of the mass ratio. So again, 1% damping ratio, and last time also we got 1% damping ratio. So now we are getting the similar results, but with the like whole numbers. So I have planned to use this kind of optimization strategy for the different design variables. So now what should be the ranges of the mass ratio range is okay. Like we are giving the mass ratio in terms of the maximum mass ratio. But the damping ratio, what should be the range of damping ratio? I was not sure. So I checked the different literature on optimum damping ratios of TMDs. Obviously, we do not have it for the hybrid systems, but for the normal damped single degree of freedom systems or multi-degree of freedom systems, we have some papers of, say, Warburton from 1982. So from there, I saw the different damping ratios value, and I found that mostly for even 2% mass ratio, until 2% mass ratio of the TMD, the maximum damping ratio is around 30%. So I just capped the maximum damping ratio to 30%. So now using this ranges, again I run the optimization problem, and again I got like similar results, because as it is the maximum, the damping ratio was lesser in case of the first TMD, and the second TMD is not of much importance here, whether it is 25 or 47, because the mass ratio is very small. So with this, like I see that the optimization problem is now working for the like Bayesian optimization, whatever the results that I have obtained from this code. So this is the like default parameters, and this is also the modified. So in the default case, we have maximum of 30 like objective evaluations and 10 seed points. But I have also checked with modified, and the results are quite similar using default and modified. So now the optimization method is working fine, I think so. So next I will now plan to like take the contribution of all the different earthquakes and get the like optimum results. So before doing that, one more check I wanted to do is that whatever optimization results that we are obtaining here, is that matching with the Stera results also. So whatever like optimum results we are getting here, I matched that with the Stera results. So I matched first of all the MATLAB results of single degree of freedom system, the MATLAB results of multi-degree of freedom system, and the Stera results. So there is some differences in the unbonded isolator case. I still couldn't like figure out why this difference is there. And this is the case where I have like constrained all the degrees of freedom in only one direction, in only the horizontal direction. And also I have not considered any non-linearity in Stera. So there is some small difference, I don't know. But because this difference was coming, I also tried with the state space method, like another different numerical integration method in MATLAB. But again, results are similar. But in the hybrid control system, the results are actually matching perfectly with Stera. So again, because this is matching, so now I am confident that okay, all the codes are correct, and now I can just directly extract the optimization results. So okay. So the first optimization objective that I have developed is the minimization of the mean reduction of base displacement. So actually in this objective, what I have considered is I have the 20 earthquakes. So for each earthquake, I find the base displacement with the hybrid control system and the base displacement with the only unbonded isolator case. and then I divide the base displacements to find out the ratio of the displacements, like ratio of the displacement by hybrid control divided by base isolator. And with that, I will have 20 different ratios for 20 earthquakes, and then I'll find the mean of the ratio and minimize that problem. So with that, I have tried to optimize. So this is the graph that we get from MATLAB. So this green line is actually the Gaussian process that they have developed with our design variables, and this blue line is the actual function evaluation. So it is seen that almost the Gaussian process has converged with the actual objective function, and both the observed feasible point and the estimated feasible point are actually quite similar. So it says that 92% of the mass ratio should be at the base floor with 8% damping ratio, and the second TMD at the top floor will have only 8% mass ratio and 0% damping ratio. So this was for this objective function, but then I realized that if I want to minimize the mean of the different reductions in base displacement, so it is possible that my total base displacement doesn't decrease, like the maximum base displacement does not decrease, but the reductions decrease. So which is not the ideal scenario. Like if we have the unbonded isolator with a base displacement of 820 millimeter, so we would like that to reduce to 770 or say 600 millimeter, something like that. And if the reductions in the different, like in this case what is happening, like if with the isolator the base displacement is say 450 millimeter and it is getting reduced to 400 millimeter, that also has some importance. But in the overall scenario, we want the maximum to reduce, right? So now I reframed the objective function and I tried to minimize the maximum base displacement. So for the 20 earthquakes, I just calculated the base displacement for the hybrid control system, and I reduced the maximum base displacement. And with this, again, I got similar results of say 99% mass ratio in the bottom TMD, in the base TMD with 1% damping ratio. And this I have checked with the default settings and also with the modified settings, and it is quite similar. Only 1 TMD at the base with 1% mass ratio, which was also same, by the way, for the Imperial Valley case, for the one earthquake case. And the reason is like this base displacement is actually the maximum base displacement for all the 20 earthquakes. So actually we are getting some results like this. So now after that, after considering the maximum considered hazard, maximum considered earthquake scenario for earthquakes, now I have also checked for winds. So in wind, we have 10 different wind loading scenarios. And here I have tried to optimize two objective functions. One is the minimization of the maximum acceleration at the top floor. In this case, only the acceleration of the main mass. And another is the minimization of the mean reduction of the acceleration. So again, here the the acceleration using the hybrid control and the acceleration using the unbonded isolator, we take the ratio for the 10 earthquake scenarios and then minimize the mean of that ratio. So in both cases, again, like very interestingly, as we have already seen that only for wind, we want the TMD to be at the top, and all the TMD mass should be at the top, and it should be tuned to the first stiffness of the isolator. And again, we are getting a mass ratio of 3%. So this 3% mass ratio is actually corresponds to the mass of the bottom TMD. So this means that all the mass should be concentrated at the top. So this is the results. But now in case of wind, one of the major problem is the time step. So in earthquakes, it is very the total time that is required for the simulation of say 20 earthquakes is 1200 seconds, which is around even less than half an hour. So this is very good. But for wind, so for wind with this time step, say 0.005 seconds, the time that is required is almost 1.5 hours. But this is also not a converged result, as I see from the time history. So the converged result actually gives around at 0.002 seconds time step, and this actually takes 26,000 seconds. I think maybe close to 8 hours or something. I'll just check. Yes, it's 7.3 hours, and this is the case when we are not using the unbounded isolator simulations. Like here, we are only minimizing the maximum acceleration by the hybrid control, so we don't require the simulation of the isolation system as well. So this is the case in that scenario. But when we have the mean of the reduction, so in case of reduction, we need both the hybrid control and the unbounded isolator control. So here again it just doubles, so it's 14 or 15 hours of simulation to get the results. But the a good part is like the results are showing whatever is expected. Again, for the mean reduction also, it is showing that we should have all the TMD mass concentrated at the top floor, and the damping ratio, it is giving some value 16%. So this damping ratio is actually new, because we cannot estimate this damping ratio without conducting this kind of optimization study. So and the interesting part is like although the results have not converged for the time histories using this time period, using this time step, but the optimization results are quite similar. Even for this, if we see, especially for the reduction, not for the maximum acceleration reduction. Like if we minimize the maximum acceleration, then we are actually, our objective is the value of the maximum acceleration. So in that case, this is quite different. So when the results are not converged, the values are quite different. But if we are talking about the reduction or the ratio, so when we are talking about the ratio, it is getting cancelled out. Like all the the ratio of difference using the two time period, two different time steps is almost similar. So it is 0.12, and this is also 0.1275, and the optimum results is also same. It is 1% with 16% damping ratio, 1% with 16% damping ratio. So these were the results that I have got till now. So now what I am planning is I will check these optimum results again for the different time histories, and I will see that what is kind of happening in the different earthquake scenario, so that to finally check that actually this is giving the correct result and we can rely on these results. And then subsequently I am planning to also incorporate the uncertainties in the three different in these parameters. The uncertainty in the tuning ratio of the isolate tuning ratio of the TMD, and the uncertainty in the where is it sorry and the uncertainty in the total mass ratio of the TMD. So I will work on that part, and I think if I complete that part, then I think this work is okay for one journal paper maybe. So so this was all the results that I have got so far, and now I am working on the further part.
Okay.
Yeah.
Very good.
Yes, and
So
yes,
this, how to say, elapsed time at the bottom.
yes,
It is a time by using your computer.
yes, Sensei.
So
Time by
if you use high spec computer, maybe you can reduce calculation time more.
Yes, Sensei. Yes, Sensei, that is possible. But also in my case, what I am thinking is I do not require to do like many of the optimization problems. So
Mm.
if I finalize the optimization problems, then if I only get it in 1 day or 1.5 day, also it is okay for me because I do not have to do it multiple times. But
Okay.
maybe if I require more computation, then I could use some of the lab computers also. I think there is one
Mm.
computer just behind me here, which
Okay.
I could maybe
Yeah.
use.
In my laboratory, there are two computers. I mean,
Yes.
high performance.
Okay.
We bought this computer for machine learning calculation.
Yes.
They require also a lot of time to
Yes.
find the solution. So
Yes.
you can ask Majima-san or Edison. Edison is now using this computer, I think.
Oh, okay.
Well, but they don't have MATLAB inside.
No problem, Sensei. Like MATLAB, I can download and use.
Okay. So in case you want to use high performance computer, please ask.
Yes, Sensei.
Okay?
Yes, Sensei. I will ask them. Yes.
Okay. Good.
Yes, Sensei. And also, Sensei, I have some pictures of the e-defense.
You went there.
Yes, Sensei. So this was the test setup that we have seen tested. I have also one video. So this is all actually not very big, but the objective here was different. They have two. I'll just open the laser pointer. So they have two TMDs on the roof of this gymnasium building. This is one kind of frame building. So here their objective was that since it is only one-story building, they are not like very much worried about the acceleration of the ground because that will be the ground acceleration. But sometimes if the roof vibrates very much, then the roofing actually falls and that could create problems. So they wanted to control the vibration of the roof. So they have two TMDs at these two parts, which is actually controlling the vibration of the roofs. And also they have friction dampers attached here. These are the two friction dampers. So they are tested this, and this is the video of the vibration.
So is this TMD it works against the horizontal direction or vertical direction?
I think, Sensei, this TMD is to control the vertical only, in the only vertical direction. And also they used a 3-directional earthquake motion. So there was also vertical direction, and also for the horizontal ground motion, there is some vertical motion in the roof also. So I think they were checking that. The video stopped. I just.
Okay.
Yes, and so this is the like reduction.
Not so strong earthquake.
Yes, and then we also thought that the earthquakes were not very strong. And till the end also the earthquakes did not become very strong.
If they open the experiment, they only show the moderate input. And after audience go outside, they put very strong way shaking.
Okay. Yes, okay. And also, Sensei, we saw the last building which was tested last time. This was outside e-defense. And this building was tested in that shake table in the last public showing. So this is actually part of one building. This building was put on top of this, and then this was tested. I think Majima-san has seen this experiment. This was huge because it is actually one 10-story building which was tested. But the experience was very nice, and also the earthquake memorial, Kobe earthquake memorial, that was also very nice.
Okay.
Yeah.
Oh, and the weather looks very fine.
Yes, sensei, but it was very hot, and we walked for 3 kilometers in the afternoon. So, but it was okay. There was some shade in the afternoon when we were returning, some shade of the trees.
Okay. Good. Good.
Yes.
Okay. So, is there anyone who want to talk now? So, shall we discuss next meeting?
Yes.
Let me see. Calendar. Okay, so 22nd is the deadline. For the paper. So you must submit maybe this week, Zafira-san and Ataya-san.
Okay, sensei.
Okay. で、So one day before 21st, we have a meeting.
I'm okay, sensei.
I'm okay. I'm available maybe afternoon, 1 o'clock.
Sensei,
Yeah.
I am only free this week. Next week I have to go to internship.
Okay, you don't need to attend. But you must submit paper before you, I mean, in this week.
Yes, Sensei, I will send you the cover letter.
Yeah.
After receiving confirmation, I will submit the paper with cover letter, Sensei.
So if you have any problem for submitting paper, please contact me.
Okay, Sensei, thank you.
Okay.
Thank you, Sensei.
And let's see. 21st. Well, maybe after you submit paper, 24 I'm free one day. Anytime is okay, 24. 10 o'clock.
Sensei, I have to go from 8 up to 4 every day, and I have to leave the dormitory from 6 in the morning.
Okay, you don't need to attend.
Okay, Sensei.
So Zafira-san, are you okay? 24?
21 or 24 is okay for me, sensei.
Okay. How about Saraya-san?
Yes, sir. I'm okay.
So let's make it 24.
Okay, sensei.
Okay.
Yes.
10 o'clock.
10 o'clock, okay.
Yeah.
Yes.
Okay, so see you. Have a nice day.
Thank you, sensei.
Bye-bye.
See you, teacher.